Hello everybody, today we'll be doing a hard advanced graph problem. This is our number 142, Reconstruct Itinerary. So in this particular problem, what we're trying to do is use up all our tickets. Apparently it is possible that it is possible to use them all up, and it must be available, this particular option. So it will always return true. Except we need to return the order at which we use up all these tickets. Sorry, give me a moment. All right, so so we just need to use up our tickets and figure out the way we can use it up in the smallest lexical iconic order, which means that if we have JFK, LGA comes before LGB. What does that mean? So suppose we have A, B, and then C. We want to go to B and then go back to A before, like, we go we go that then we can go from A to C, and then from C we go back to A, if that's necessary. It's not necessary, but we do not want to go from A to C, then go from C back to A, and then go to B. That is just not what we want to do. B is over here, and then we go back to B afterwards, which is not lexical. So we're gonna have to sort the tickets first. So and as you can see, this is an advanced graph problem. So we will need an adjacency list so that we can go from each particular source to each particular destination, eliminate all those tickets, and use up each ticket. So we're going to be creating that list and then removing items from that list, and moving from that particular point. The code is a little bit tricky because of how we need to iterate through the list of items, the tickets that we need to spend, but it's not too difficult of a problem. All right, let's start. So we're gonna do tickets.sort, sort all tickets, and let's create our adjacency list with a default dictionary. This is basically gonna hold a source to a list of tickets, and with that, let's create that. Source and destination in tickets, adjacency list of source is going to append the destination. Anyways, with that, let's start a result. Start with JFK, and let's move forward with running a DFS of JFK, the JFK, and returning results. Of course, we need to define our function, DFS, of our source, and yes. So if our success condition is whenever we define a recursive function, we have to define the base cases, and if the length of tickets is used +1 is equal to the results, then we have used up all our tickets, and we can return true. The reason for that is because number of tickets plus the starting point. If the source is not in the adjacency list, that means that we have not yet reached the end of the tickets, but we have run out of places to go, and so we have to return. So those are two cases. Once those base cases are passed, what we're gonna do now is look at each particular source. So we're gonna create a temp, because this is important, because we do not want to, we're gonna modify the list as we progress through our DFS call, so that we can eliminate use up the tickets. If we don't use up all the tickets and we keep reusing the same tickets, it's going to give us improper results. So let's create this temp adjacency list of the source, and this particular source is going to be our temp list. So we're going to do this I and the destination in the temp. We'll have to enumerate enumerate the temp. The reason why we need to enumerate the temp is because adjacency list at the source is we're going to pop at I. That's right, we're going to pop at I. We're going to pop at that particular index. Because we need to remove that particular item. Interestingly enough, if we pop at I, the location of I is set to nil, but other locations still valid, which is pretty interesting, considering that that would be necessary for this to happen. So anyways, so we're going to set our results dot append our destination, and we're going to run if DFS of the destination is going to be true, then return true. Otherwise, that means that we kept going down a rabbit hole, but we returned false. That means that we need to roll back. We need to backtrack. Results dot pop, and we also need to add this back to insert this back into the same place. And with that, we should be able to go through the entirety of this particular DFS call, and we should be good to go. Oh, one more. Yeah, that's good. Let's submit. There's one more thing that I would like to add about this particular problem, is that if we do not if we do not get an answer, like if it's not possible, if those are one of the results, we should return a false down here, and we should do it if DFS, then we return results, and then otherwise return none. But that's not the case. So we're gonna keep this, like, we keep this code. Right, and that's it. It's a pretty simple problem. Unique ways of using an array that we're not used to. That's pretty interesting. Remembering always considering base cases, and looking at what we're trying to do, remembering those types of things. So let's summarize those types of things. Always go in lexiconic order. Use each ticket via node, and remove tickets from usage. Backtrack to and add ticket back. One last thing is that the O of n, how long would this take? So we need to go through each ticket and create all the edges. So that would be O of the number of tickets, O of n. Here, what we're looking to do here is go through each particular path down a DFS call, and we're going to be going through like each edge, and that means that we're not visiting the edge once. We could be going through many edges multiple times, and we're backtracking here. So what would that be? Let's see. Let's think about it. So backtracking. Well, let's talk about the space. Of course, is the number of tickets, is O of n, and the time is going to be definitely going to be O of n. but I think we have to multiply this against something to a certain power of some sort. I'm not sure exactly. So I'm gonna. I mean, yeah. I think it goes to the depth of the tree and comes back. So, however deep the tree goes. So, because we're gonna go into the tree and then come back out and then go back into the tree, and yeah, that's the tree depth, and the depth is, well, n, so it's n squared, I think. I might be wrong, so let me know if that's incorrect. And we will come back and proceed with the proper solution. Actually, let me just go into discussion and we'll pull that up right now. So let's just grab that. So time complexity, time and space. Oh yeah, VV log V. He's not sure either. Well, yeah. Anyways, it looks like we're not really very sure, but that's what I'm gonna go with. N times n. I don't know where the log n comes from. So yeah, not really sure. So let's just take a look. Maybe somebody has it. Yeah, looks like it's everyone believes it's v log v plus e. So yeah, I don't think anyone's very sure. Yeah, but I think it's O of n times n. Anyways, if you enjoyed the video, like and subscribe. Want more videos, check the link in the description below. Thank you very much, and I will see you in the next one.